Okay, so anyone have a thought on what they think is the most likely thing out of this list?
J.
Okay, Kanisha here and Paige put J, meeting someone who has the same birthday as you, and that is actually correct. There is a 1 in 365 chance that you will meet someone with the same birthday. And actually, if you're on Facebook, you'll start to see how common it is to share a birthday with someone, or your friend sharing a birthday with 3 people that you know. And so that is actually the most likely event to happen. Anyone want to take a guess on the second most likely event to happen? Anyone want to be brave and take a guess?
I put H.
You put H, being attacked by a shark. Well, being attacked by a shark is 1 chance in 3.7 million. And it's not the next one. The next one, which surprised me actually, is G. Being born with 11 fingers or toes. You have a 1 in 500 chance of being born with 11 fingers and toes. That absolutely shocked me. Of course, I got this all from the internet, so hopefully it's accurate. So number 2 is being born with 11 fingers or toes. Finding a pearl in an oyster is 1 in 12,000, and it's the next likely event. Are you close on that one? Okay.
I had F and G.
Okay, you had F and G reversed. Nice. Anisha's good at probability, apparently. All right. What about number 4? Anyone got a guess? You put what? E? That's not next. D, I've got an H and an A, and actually A is number 4. Being struck by lightning is 1 in 15,300. It's in your lifetime, being struck by lightning. All right, what about number 5? Any thoughts on what's next? Okay, D says B. It's not B. It's not being in a plane crash. It is actually finding a blue lobster in the ocean. And that's 1 in 2 million. So it's a pretty big jump from number 4 to number 5. And as you're observing, it's less likely as these numbers become bigger and bigger. 1 out of whatever, as that number gets larger, your probability is less. And number 6 is actually being attacked by a grizzly bear in Yellowstone Park. That's 1 in 2.7 million. And then someone liked the shark earlier. The shark is next. That's 1 in 3.75 million. So you're more likely to be attacked by a grizzly bear than be attacked by a shark. Although neither would be things we would want.
Hey, Mary, can I ask you a question?
Yeah.
Because I'm learning right alongside the students today.
Yeah.
Thanks. So when you say 1 in whatever 15 million, does that mean 50 million times you're in the same situation, or 15 million other people and you're the one?
Well, it's that idea that when they look at lightning statistics and they count basically how many people get struck by lightning over the total number of people, that one out of, let's say there's 65 million people and there's so many lightning strikes, they literally just divide it out. And so the idea is not, and we'll talk about this in just a minute. The idea is not if you lined up 15,300 people, one of them for sure would have been struck by lightning. But odds are if you polled 15,300 people at the end of their life, the lightning one's a little hard because it's in your lifetime. If you
Okay.
15,300 people right before they're about to die, one of them probably would have been struck by lightning.
Okay. Thanks.
So yeah. Okay, number 8 is our plane crash. 1 in 11 million. You are much more likely to be in a car crash than in a plane crash. So for those of you who are scared to fly, odds are you're not going to be in a plane crash. All right, number 9. Okay, so we have 9 and 10. We have winning the Powerball jackpot or winning it. Hopefully everybody's old enough to remember the McDonald's Monopoly game. Maybe not. That might have been a bad one to pick.
Actually, I do.
McDonald's used to have this game where you'd get these little, of course, you probably know about the game Monopoly, and you would get these little cards and that were different places on the Monopoly board. And if you got so many, you'd win money and you could win $1 million. So winning the Powerball jackpot or winning $1 million in McDonald's and Monopoly game, obviously when it was offered, which one do you think is more likely?
I would say the McDonald's.
That would be incorrect.
Really?
It's actually more likely to win the Powerball jackpot, and your odds are 1 in 292 million. That's a lot of lottery numbers, my friend, if you want to win. And number 10 is actually winning $1 million in the McDonald's Monopoly game, and that was 1 in 45 million. Okay. So this is hopefully just kind of a fun activity to start thinking about probability and what it means. Obviously, we're going to get more in depth, but obviously our behavior doesn't always reflect this. We might be scared of sharks. Likelihood is if you're in the ocean, you're not going to get bitten by a shark. Some of us are more scared to fly than to drive, but the likelihood of actually being killed in a car crash is much higher than being killed in a plane crash or even being in a plane crash. So I hope none of those bad things happen to you, and I would wish that some of those good things would happen to you. But this is just, like I said, as our number gets bigger, 1 out of 2 million is much more likely than 1 out of 11 million, although still not very likely. So if you take a look at the next page, we're going to watch a video that kind of introduces probability, and then we'll work through what else is on this page. So let me get this video over here. I think I've played through the ad. And you guys hear that?
Hi, I'm Rob. Welcome to Math Annex. In this,
Okay, I can hear this in Page. Can you guys hear it online?
Are we supposed to see
Yeah.
it too, or just hear it?
Can you see it? You should be able to see it and hear it.
We can't see it.
You can't see it. That's interesting. That's because I never shared my screen. That would be why. I thought you guys could see the paper I was writing on, so I apologize for that. Okay.
We
So,
put the paper up ourselves. We're good.
okay, good. So that was, if you want those, actually, if you missed any of these, on the last page of the packet are the answers, and I wrote those all out, but I apologize. I thought that you could see, I forgot I had not shared my screen.
Yeah.
I'm out of practice here, not having taught in a while. Okay, so let me get. All right, now you should be able to see the video, yes?
Yes.
Okay,
Yes.
now we're gonna turn it on.
this video, we're going to learn about how to do math with things that only sometimes happen. They might be likely or unlikely. we're going to learn about probability. Usually in math, we deal with things that always happen the same way. They're completely certain. Like if you add 1 and 1, you're always going to get 2. If you multiply 2 and 3, you're always going to get 6. There's no uncertainty at all. But in the real world, things aren't always so predictable. Take a coin toss, for example. We can't predict whether it'll be heads or tails. It's unpredictable or random. And that's why some people will flip a coin to help decide which of two things to do. That's how I make every decision in life. Why am I not surprised? Oh no. Good luck. But even though we don't know what each coin flip is going to be, we do know a few things about it. We know that with a fair coin toss, that heads is just as likely to show up as tails. The probability of an event, like getting heads or getting tails, is a value that tells us how likely that event is to happen. With our coin toss, since each side is just as likely, and there's only 2 sides to a coin, if we flipped a coin a lot of times, we should expect that about half the flips will be heads and about half the flips will be tails. That means that the probability of flipping heads is the fraction 1/2, and the probability of flipping tails is also 1/2. Let's look at this in a little more detail on something called a probability line. It's a number line that goes from 0 to 1. A probability of 0 means that an event cannot happen. It's impossible. And a probability of 1 means that an event is definitely going to happen. It's certain. That's why the probability line only goes from 0 to 1. An event can't be less likely than impossible, and it can't be more likely than certain. A probability of 1/2, like with our coin toss, means that an event is just as likely to happen as it is to not happen. A probability less than 1/2 means that an event is unlikely, and a probability greater than 1/2 means that an event is likely. Oh, and in addition to fractions, it's also common to write probabilities as decimals or percentages, since you can easily convert between those three. A probability of 0 is the same as a 0% chance of something happening. A probability of 1/2 is the same as a 50% chance of something happening. And a probability of 1 is the same as a 100% chance of something happening. Now that you know how a coin toss works, let's see an example of an event that is unlikely, using something a little more complicated than a coin. Let's take a look at dice. A standard die has 6 sides numbered 1 through 6. When you roll it, any of those sides is just as likely to come up as the others. That sounds a lot like flipping a coin, doesn't it? Each side of a die is just as likely to come up as the others, and each side of a coin was just as likely to come up as the other. So you might expect that the probability of rolling a 3 is 50%. But remember, with a coin toss, there are only 2 possibilities, heads or tails. With dice, there are 6 possibilities, and that's going to make a difference in its probability. One way to think about it is that it's certain that one of those 6 sides will land facing upwards, which is a probability of 1 or 100%. But since only one side can face upwards for a given roll, we have to divide up that value among all the possibilities. In the case of a coin toss, since there were only 2 possibilities, we had to divide the probability by 2. 1 divided by 2 is 1/2, which is the decimal 0.5 or 50%. But with the die, we need to divide the probability up evenly between 6 possibilities. 1 divided by 6 is 1/6, which is equivalent to 0.167, or 16.7%. So that would be right here on our probability line. That means it isn't likely that I would roll a 3, for instance, but it's just as likely as rolling any other number. And since all 6 numbers have the same probability, each number should come up about as often as the others. To see if they do, I'm going to conduct some trials. That's an excellent argument. Allow me to deliberate. Guilty. Actually, when dealing with probability, a trial, which can also be called an experiment, is a process that has a random outcome, like tossing a coin, or rolling dice, or spinning a spinner. And the outcome of a trial is what happens in that particular trial, like flipping heads, or rolling a 3. So I'm going to conduct several trials by rolling a die multiple times and keeping track of how many times I roll each number. Aha! You said that each number was going to come up just as often as the other numbers. But look, there's more 2s than there are 5s. How do you explain that? Well, remember, we're dealing with things that are random. They're unpredictable. We can't know exactly what will happen, just what will happen on average. So now I have to calculate the average? Well, when we say on average, we mean that the more trials you do, the closer you get to the expected probabilities. Keep watching. There. Now that we've done a lot of trials, you can see that our totals are much closer to what you'd expect them to be. I guess you're probably right. That's one of the really important things to keep in mind about probability. If you do just a few trials, the results might not end up very close to what you'd expect. In fact, they could be way off. But if you do more trials, you increase your chances of reaching the expected probabilities. There's another thing I should point out. Remember the probability of flipping heads is 1/2, and the probability of flipping tails is 1/2. The probability of rolling a 1 is 1/6, and the probability of rolling any other number on the die is 1/6. If you add up the probabilities for the coin flip, you get 2/2, or 1. And if you add up the probabilities for rolling a die, you get 6/6, which is also 1. And that's not just a coincidence. If you add up the probabilities of all possible outcomes of a trial, the total is going to be 1, or 100%, because it is certain that at least one of those possibilities will happen. Let's look at some more examples. For these examples, we'll use a spinner. If we had a spinner with just 6 equally sized sectors, the probabilities would be exactly the same as with dice. So we want a few more sectors. There, that's more like it. Now we have 16 equally sized sectors. So what's the probability of spinning a 12? Well, just like with dice, where we had to split up the 100% between all 6 possibilities, we'll do the same thing now, but we'll split it up between 16 possibilities. So the probability of spinning a 12 is 1/16, or about 6%, which is right here on the probability line. We can see that the probability of spinning a 12 is less likely than the probability of rolling a 3. And that makes sense because there are more possible outcomes with our spinner. But what if we color some of the sectors a different color and we want to know the probability of spinning a certain color? Now we have 5 sectors colored blue and 11 sectors colored yellow. So what's the probability of spinning a blue? Remember how with the coin toss, we ended up with the fraction 1/2, and with the die roll, we got the fraction 1/6? In both cases, we had 1 as the numerator, and that's because we were interested in only one of the possible outcomes, like the probability of flipping heads, or the probability of the number 3 being rolled. But in this case, the top number of our fraction will be 5, because any of these 5 sectors will give us the color we want. And the bottom number will still be the total number of possibilities, which is 16, because that's how many total sectors we have.
So I'm going to stop it for just a second. So that probability of 5/16 would say that if you spun this spinner 16 times, on average, you would expect to get a blue about 5 times. But just like with the dice, if you spin it exactly 16 times, you're probably not going to get exactly 5 blue sectors. But over time, with lots of trials, you should get closer and closer to that number. That's less than half of the dial that's blue, and so less than half of the time you should get a blue. So if you think about like playing cards or rolling dice, like if you're in Vegas, all those payouts are based on how likely something is to happen. So if something has a really big payout in a casino, it means it's not very likely to happen. Not impossible, but not likely.
So the probability of spinning a blue is 5/16, or about 31%. That's still considered unlikely, but it's more likely than spinning a specific number. And this method will work for figuring out the probability of any event. You just make a fraction with the numerator as the number of outcomes that satisfy your requirement, and the denominator as the total number of possible outcomes. Let's try the same method to find the probability of spinning a yellow. Our top number should be 11 because there's 11 yellow sectors, and our bottom number should still be 16. So the probability of spinning a yellow is 11/16, or about 69%. Now we finally have a probability that's considered likely. And it makes sense because you can see by looking at our spinner that it's more likely to spin a yellow than a blue. And you'll notice, if we add up 5 over 16 and 11 over 16, we get 16 over 16, or a probability of 1. So that's a good sign that we did it right. Let's look at another example. Suppose we have a bag of marbles. There are 3 green marbles, 7 yellow marbles, and 1 white marble. If we mix them all up and pull out a marble at random, what's the probability of it being green? Well, the top number of our probability fraction will be 3 because there's 3 green marbles. So there's 3 outcomes that get us what we want. And the bottom number will be 11 because there's a total of 11 possible marbles that we could pull out. So the probability of pulling out a green marble is 3 over 11, or 0.27, or 27%. It's right here on the probability line. That means it's unlikely. And that makes sense because you can see that it would be less likely to pull out a green marble than one of the other ones. Let's try this again for calculating the probability of pulling out a yellow marble. This time, the numerator of our fraction will be 7 because there's 7 yellow marbles. The denominator will still be 11 because there's still 11 marbles total. So the probability of pulling out a yellow marble is 7 over 11, or 0.64, or 64%. Another example of an event that's likely. How about pulling out the white marble? Well, the top number will be 1 since there's only 1 white marble, and the bottom number is still 11. So the probability of pulling out a white marble is 1 over 11, or 0.09, or 9%. Not very likely. And if we add up these probabilities, we get 11 over 11, or 100%, just as we expected.
And remember that as we add fractions, we have a common denominator of 11 that stays when you add fractions, and you just add the top numbers. 3 plus 7 plus 1 is 11. So quick fraction review there.
All right, so you should have a pretty good handle on basic probability now. You just have to remember to make a fraction with the numerator being the number of outcomes that give you what you want, and the denominator being the total number of possibilities. And we learned about the probability line, and that a probability can't be less than 0 or greater than 1, or 100%. We also learned that the more trials or experiments you conduct, the closer your results will get to the expected probabilities. Of course, the way to get good at it is to practice, so be sure to do a lot of problems on your own. As always, thanks for watching Mathantics,
Okay, let me.
and I'll see you next time. And I sentence you to 5 years hard labor.
Okay, let me drag him out of the way. So any thoughts or questions after that video?
I'm just a little confused on like the wrapping it.
On the number line?
Yeah.
Okay, we'll take a look at that in just a minute. So Kanisha here and Paige asked about just the number, the probability line, and we will get to that. So I put on here a definition. If you ever wanted to go back and look at this, that if you open the I'm missing a word here. If you open the file, you should be able to click on this YouTube video. So probability, as he defined it, is how likely it is that something will happen. 0 is it won't happen or it's impossible. 100 means it's certain. And probably the most common instance of you dealing with probability on a day-to-day basis, if you check the weather, some of you may not, but I check the weather every day. And one thing I look at is what's the chance of rain? If I'm planning to go on an outdoor hike and there's a 90% chance of rain, that will mean that I will either change my activity or I will dress differently than if there's a 10% chance of rain. And so that is probably a context that you're very familiar with probability. And you know that the higher the chance of rain, the more likely it is going to rain on your activity. But I'm sure many of you have gone somewhere where it said there's an 85% chance of rain, but it doesn't rain. It's not a guarantee. My husband also says in his next career, he's going to be a weatherman because you can be wrong most of the time and keep your job. But that's where you're used to seeing probability on a day-to-day basis. And he talked about probability is typically expressed as a percent or a fraction. And on your nice nifty calculator that you get to use on the GED, I've got some keystrokes of how you can enter a fraction. And so if you want to enter 40%, you would enter, increase the size of this, you would enter 40. And then the green second key is up in this upper left-hand corner. And then if you look above the open parentheses, there's a green percentage. And so when we push that green second key, you tell it that the next key I push, you want the green thing that's above the key. And so that's how to enter 40%. If I want to change that to a fraction, there's the double arrow key that is right above the enter and right below the plus. I hit the double arrow key and enter, and it changed 40% to a fraction, 2/5. And then if you want to make that fraction into a decimal, you push the double arrow key and it will change 2/5 to 0.4. And if you're a person who really struggles with percents, decimals, and fractions, this calculator is a powerful tool that you really need to learn how to use. And then if we want to go back to percent, if we hit that green second key and then the closed parentheses, above it is an arrow to parentheses, and then enter, it'll take us back to 40%. So that's a tool that you can use if you're struggling, if you've got a problem that you've figured the fraction, but it wants the percent, the calculator can actually calculate it for you. Okay, so he talked about the probability of a single event is the number of desired outcomes. I think he said the number of outcomes that are what you want on the top and the total number of outcomes on the bottom. And so that's where our flipping our coin, there's two sides, that's our total outcome. And we want heads, let's say, one head out of two or one tail out of two. And so this probability line is just a visual picture of things that are 0% that are impossible, or 100% one, which is certain. I do realize that when you think about 100% chance of rain, the weatherman's telling you rain is certain, but again, like my husband says, he's often wrong and still keeps his job. So, but basically, if you see 100% rain, you know it's pretty darn certain it's going to rain at some point. Okay. And so if you can picture this number line, the idea that flipping a coin is 50% chance of heads, 50% chance of tails. And those are, you might say, even odds or equally likely would be words you might use to describe this scenario. And then anything that's below here, we would call unlikely or less likely. And then anything above 50%, we would call likely or more likely. And so if you can kind of picture this, sometimes that can help you with probability problems, particularly probabilities of a single event. And so, Kanisha, you said you had a question about the probability line. Is there something specific?
It's just like marking it on there. That's my big.
Okay, well, if you think about it, so halfway between 0 and 1, we have 1/2 or 50%. And so basically, they're kind of estimating where to put these. And it's not as important. I don't think you'd ever be asked to plot it on the line, but it's an idea of, in your mind, thinking how likely is this? Is it above 50% or below 50%?
Okay, yeah,
But basically, like if you cut 0 to 1/2 in half, that would be 25%. And then 12.5%, you could cut this line up just like a ruler. You think about a ruler between 0 and 1. And so let's think for a minute, what's an example of something that has a probability of 0? Anyone come up with something, an example?
maybe getting hit by an asteroid.
Getting hit by an asteroid is, I wouldn't say it's probably exactly 0, but it is mighty, mighty close. It's just been in the news recently that someone's house got hit by I guess it was a meteorite. Is that the same as an asteroid? I'm not sure. But that's something to be extremely close to 0. It's actually kind of hard to find out things, I guess. What about flipping or rolling one die and getting a 7? Is that
Yeah.
possible?
No, that's not possible.
Okay, so that would be something that's impossible. Okay, what about finding a real live pig that can sing an opera? Probably not very likely. Okay, so, but actually in some cases, it's really hard sometimes to think of something that has a 0 probability.
How about me flying home with my wings, my arms?
That would be a good example of something that is 0 probability. Very nice. Okay.
Oh,
So most probabilities that we deal with occur between 0 and 100. The weather, sometimes they do say there's a 0% chance and sometimes they say there's 100, but you've got to think of usually some kind of ridiculous things to be absolutely 0%. What about 100%? Something that's certain, it's guaranteed. As you think of that, you realize there's not a lot of things that are guaranteed in this life, are there? You could say there's 100% chance that I'm going to go eat lunch today, but you know, there is a possibility you could drop dead on the way there. Not likely.
I was just about to say like death. Death is 100%.
Okay, that's a good example that you're going to die someday is probably about 100%.
Yes, there's vampires or something.
Again, then you can go off into wild examples. A basic example of something that would have a probability of something of 100% is if I flip a coin, I'll get heads or tails. And then you could say, well, what happens if it gets stuck in a crack and it doesn't, you know, doesn't land on one side or the other, and that should say 100%, not 100. It's a typo on my part. Okay. Okay, so most of the times we don't spend our time thinking of things that have a 0 or 100%. We actually calculate probabilities. And cards and games are a place that have lots of probabilities. If you're a good card player, then you may be good at least considering probability, because you're a whole, like, let's say you're playing poker, you're a whole lot more likely to get a pair of matching cards than a full house. Okay. And so in your mind, if you've played games where you're trying to collect cards for something, you may have this sense that obviously there are some cards that are combinations that are harder to get than others.
I actually played a lot of poker.
Okay, poker, or if you play dice, if you play even Yahtzee, the game Yahtzee, you may start thinking about likelihood of things. And I see another typo. This should say hearts. Okay, so if you're not familiar with cards, a deck of cards has 52 cards. There's 13 red hearts, 13 red diamonds, 13 black clubs, and 13 black spades. And so if we look at what is the probability of drawing a red card from the deck, to answer that, we need to make a fraction for starters with the total number of possibilities on the bottom. So how many total possibilities is how many total cards there are? There are 52 cards. And now we want a red card. So the question is, how many cards are red? More than 13. How many cards are red? We've got 13 red hearts. Very good. And we've got 13 red diamonds. So we have 26 red cards out of a total of 52 cards. Okay. And you can make a fraction in your calculator. The fraction key is 3 keys above the 7. And you can put in 26 and then toggle down and do 52. And if you press enter, that will change or reduce the fraction for you. Basically, half the cards are red, right? Half the cards are red. And so 26 out of 52 reduces to 1/2, which you probably know is 50%. And so on our probability line, I have the same chance of rolling a heads or tails as I do drawing a red card out of a deck. And so we think about then what's the probability of drawing a black card from the deck? There's still 52 cards in the deck. And 26 of them are black, which is also 1/2. And D, you're right. You pointed out earlier that 1/2 is 0.5. And it would be that here as well, or 50%. So number 5, what's the probability of drawing an ace from the deck? Okay, our deck still has 52 cards. And how many aces are there in a deck of cards? Who are my card players?
4.
4. There's 4 aces. There's an ace in every suit. There's a ace of hearts, ace of diamonds, ace of clubs, and an ace of spades. So there's 4 aces out of 52. So if I were simply to pick a card at random, there's a 4 out of 52 chance that I would get an ace. That fraction probably doesn't mean a lot to most of us, but we could change that fraction to reduce it. 1 out of 13 chance that we would draw an ace. We could hit the double arrow key and turn that into a decimal. I'm going to just round it to 0.077. And then I could also make the calculator turn that into a fraction for me. And you can see it's 7 points. I'm just going to round it to 7.7. If you remember your decimals and fractions, you might remember that to turn a decimal into a percent, you just move the decimal point 2 places to the right to get a percent, or the calculator will do that for you. Okay. And then number 6, the probability of drawing a red king or the 2 of spades. Okay, I still have a deck of 52 cards. The question is, how many possibilities are what I want? A red king or the 2 of spades? How many possibilities are what I want? There's more than 2. How many red kings are there? There's the king of diamonds. There's the king of hearts. Or I want the 2 of, see if I can draw a spade. Or the 2 of spades. Those are the 3 cards that I want one of these 3, right? And so there's 3 choices that I want out of 52. There were 4 aces in my deck, but there's only 3 cards that are a red king or the 2 of spades. And in my calculator, again, I can make a fraction. I push the key that's 3 over the 7, 3 above the 7. I put 3 on the top, 52 on the bottom. If I press enter, it gives me the same exact fraction. That means that that fraction can't be reduced at all. It's in the lowest terms. But if I push the double arrow key above the enter, it'll take me to the decimal. So I'm gonna round. I'm gonna look at this 7. Looks next door. It's a 6, so the 7 becomes an 8. So I'm gonna round that to 0.058. And then I can turn that to a percent by moving the decimal 2 places or pushing the second and the closed parentheses. And it will tell me that it's 5.76, and that 6 would round the 7 up to an 8. So there's only almost a 6% chance that if I draw a deck out of a random deck of cards, a regular deck of cards, if I draw one card at random, there's only a little less than 6% chance that I would get one of these cards. And what that means is if I did this 100 times, pick the card, see if it's one of these 3, put it back, pick another card, see if it's one of these 3, put it back, shuffle them up, pick another card at random. If I did that 100 times, you'd expect that 5 or 6 times we might get one of these cards. Whereas if I pick at random, about half the time, I'm going to get a red card. And about half the time, I'm going to get a black card. Questions on this? This is called the probability of a single event. Any questions or thoughts? If we look at our probability line, everything that we
Sorry.
calculated.
Mary, I had a question.
Yeah.
Can you hear Dee?
Yeah.
Just barely.
She wants to know if you could just review how to do the fraction again on the calculator.
Yeah, sure. How to enter the fraction?
Yes.
Okay, so if you look at the 7, 3 keys above the 7, you'll see a fraction. There's n over d.
Right.
So you push that and it makes what's called a fraction template on the calculator. And so let's say I want to put in the fraction 6 over 8. I would type a 6 in, and then this round key here, I can toggle down, up, left, and right. I want to toggle down to the bottom of the fraction. And now I'm blinking in the bottom of the fraction. I type in my 8. To get out of the fraction, I use this round key and I want to go to the right. And now I'm out of the fraction.
Oh, okay.
And from here, you can reduce it by just pressing enter. And you can turn it to a decimal by pushing the double arrow key.
That work?
Yeah.
All right.
I was 2 seconds to try and get the decimal, but then it was putting the other number in front of it, so I got it.
Okay, any other questions about the line, about probability, single event probability? I'm going to give you a chance to practice some of these here in a bit. All right, so the GED people say that in general, most people do pretty well on the probability of a single event. And where most students have the most trouble is the probability of what's called a series of events. That, like, I'm going to roll a die and flip a coin, or I'm going to flip a coin multiple times. And how do you find the probability when you've got multiple events happening or a series of events? And basically the answer is all you do is you multiply the probabilities of each individual event. So for example, if I want to know the probability of rolling a die and getting a 4 and flipping a coin and getting heads. So I want both of those events to happen. I'm going to roll the die. I want a 4 to come up, and then I'm going to flip the coin and I want a head. Combining those two probabilities in this series of events, the key operation is to multiply. Okay, so the probability of rolling a 4, just like he did in the video, each side of the die is equally likely to come up. There's 6 sides. So the probability of rolling a 4 is 1 out of 6. And the probability of getting heads on our coin is 1 out of 2. And so to find the probability of both things happening, you multiply them. Now, quick multiplication reminder, when you multiply fractions, you multiply across the top and you multiply across the bottom. Remember, that's different than adding. When we added fractions, we kept the same number on the bottom. But multiplying fractions is actually easier. You can also multiply fractions in your calculator. So let's see if you can, let's go through the steps to multiply these two fractions. You would hit the template for the fraction, which is 3 keys above your 7. You're blinking on the top of the fraction, so you type in 1, toggle down, and put a 6. Now we need out of that fraction, so you hit this circular key to the right. And now you can see the cursor is out of the fraction. We're going to multiply that by another fraction. And I'm going to fill in 1 on the top, toggle down to the bottom, and put in a 2. And then this circular key to the right will get me out of the fraction. So I want to multiply 1/6 times 1/2, and I get 1/12. Now, if you want to turn that to a percent, remember, if you look at above the close parenthesis key, right above the 9, it has an arrow to %. So if I hit the second green button and then the close parentheses, it's going to take 1/12 to a percent. And so it's a little more than 8% likelihood. In other words, not very likely that if I roll a die and flip a coin, that I will get a 4 and a heads. It's not very likely, only 8% chance.
I have a question, Mary.
Yes,
That green key with the second?
Yeah.
That means like a second operation, basically,
it means,
or a second entry.
well, no, do you see all the things in green above the keys?
Mm-hmm.
It means if you want the operation that's in green, you have to
Mhm.
push the second first. So it's
Okay.
like your shift on a keyboard where you want a capital letter.
Mm-hmm.
Okay, so if I look above the, if I look above this parentheses key, there's a %. So if I just push this open parentheses, that's what it's going to give me.
Mm-hmm.
But if I type in 40 and then I want the thing in green, so I push the green key first and then instead of the open parentheses, it gives me the % that's above it.
So you press the second button first and then the open parentheses for green?
Yes,
Okay.
the other thing that's in green.
Thank you. You don't press them at the same time.
No, you just hit one and then hit the other. You might be able to do it at the same time. I don't know.
Okay,
Like it'll let you do that.
thank you.
All right, so let's consider the probability of flipping a coin 3 times and getting heads every single time. Do you think that's likely or unlikely? Flip a coin 3 times in a row, get heads every time. Okay, Kanisha here in Page says unlikely, D says unlikely, and I would agree with you. Okay, but let's calculate the probability. So the probability of getting a heads on the first time I flip it is what? Right, 1/2. Okay, so now I flip it again. What's the probability of when I flip it now that I get a heads? Same thing, very nice. And then the third time, same thing. Because this event doesn't impact others. I can keep flipping, and the fact I got a heads the last time doesn't change what's going to happen the next time. And so I take these and I multiply them. And remember, for fractions, I multiply across the top. 1 times 1 times 1 is 1. I multiply across the bottom. 2 times 2 times 2. Not 6. That's the easy thing to say. 2 times 2 is 4. And 4 times 2 is 8. It's a very common mistake, my dear. And so the probability of getting a heads 3 times in a row is about 1 out of 8. Again, we can change that, put that into our calculator if we want. Put in the fraction. If you just hit enter, it's going to tell you that that fraction is already reduced. To get it to a decimal, you push the double arrow key. That would be your decimal. It's below 50, below 0.5, so it's definitely less likely. And if I push the second and the close parentheses, it'll take that decimal to a percent, which remember, you can just move the decimal point 2 places to the right, or you can put it in the calculator. And there's about a 12.5% chance that if you flipped a coin 3 times in a row, that you would get heads every single time. Okay. So these 2 examples are examples when the outcome of the first thing does not affect the outcome of the next one. For example, when I roll the die and I flip the coin, when I roll the die, it has no impact on what the coin flip is going to be. When I flip the coin 3 times, if I flip a coin here and then I flip it again, what happened previously doesn't change what the next thing that happens. But sometimes one event can affect the next event. And that's kind of the next level of this idea of probabilities that are in a series. And so basically there's 3 kinds of problems. There's a probability of a single event, okay? Just a plain and simple single event. For example, if you read that Chad has a bag of marbles with 3 black marbles, 8 green marbles, and 6 blue marbles. The probability of a single event would be something like, what's the probability of reaching into the bag and drawing out a green marble? Single event. How likely is it that if he draws out a single marble, he's going to get green? So this is where we make our single fraction. We look at how many events, how many outcomes are what we want. In other words, how many ways can I draw a green marble over the total? So there's 8 green marbles out of 17, and you get 17 by adding 3 black marbles plus 8 green marbles is 11 marbles, and 6 blue marbles makes 17 marbles that are in the bag. And so the probability of a single event like drawing out a green marble is nothing more than the fraction 8 over 17. Which I can put in my calculator. It cannot be reduced because when I press enter, it gives me the same fraction. I can push the double arrow key and it tells me the decimal is 0. I'm just going to say 47.47. Well, I'm getting that because I have a decimal 0.47 and the next number is 0. So that 0 keeps the 7 the same place. And then if I turn that into a percent, that's 47%. And this should kind of make sense. Almost half the marbles are green. So almost the probability of drawing out a green should be almost 50%. Okay. This problem, like number 2, is your probability of a single event. It's your simplest, most direct probability problem. Number 3 is the probability of a series of events that don't affect each other. Okay, and that example would be Chad's going to take that bag of marbles. He's going to draw out one marble. He's going to put it back, and then he's going to draw out another marble. In other words, after he draws out the first one, he's going to restore the bag to the original scenario and then draw it out again. And so the first marble draw has no effect on the second marble draw because all the marbles are still back in the bag. And so this is a series. So we're going to have 2 fractions that we're going to multiply together. And we want to know the probability that he gets a green marble first. Well, we already know the probability of getting a green marble because that's what we just figured out in the first problem. There's 8 green marbles out of 17 in the bag. So he draws out a marble, puts it back, and then he draws another marble. What's the probability that he draws out a black marble? Out of, yes, 3 out of 17, because there's 3 black marbles and there's still 17 marbles in the bag because he put back the one he drew first. And so this is the probability of a green, and we're going to multiply it times the probability of a black marble. Remember, with probability, we multiply across the bottom, multiply across the top, or 17, we can put it in the calculator if you want. We create a fraction template. And we enter our first fraction. And then we tell the calculator we're going to multiply that by another fraction. And that fraction is 3 on the top and 17 on the bottom. And you get 24 out of 289, which is a fairly unlovely fraction. We can press enter to see if it will reduce that fraction for us. And it does not. I don't think that fraction cannot be reduced actually, because 17 and 17 are both prime. So that can't be reduced, but we can change it to a decimal. I can just hit the double arrow key down here and it'll turn it to this decimal. I'm going to round. I'm going to say 0.083 because next door to the 3 is a 0. So I'm going to round it to 0.083. I can move the decimal point 2 places to the right, or I can push second and the close parentheses to say that I want to take that number to a percent. And so it's about 8.3%. So this third problem is just like the 2 at the top. My rolling my dice, my flipping my coin, those 2 events don't affect each other. An example of when they do affect each other, and you have to be really, really careful because these are the problems that they're going to get you on, is sometimes the series of events do affect each other. And let me show you how this works. Chad is going to randomly select a marble, and then he's going to pull out a second marble without replacing the first. Okay, and that's what has the impact is after he draws out the first marble, how many marbles are left in the bag for the second draw? There's only 16 marbles left in the bag after the first draw. And so what he did by drawing out the first marble and not putting it back leaves fewer marbles in the bag, which is going to impact the probability of pulling out the black marble second. Okay, so we're going to start the same way. We're going to multiply two fractions, the probability of the green times the probability of the black, but it's going to look a little bit different than the previous problem. On his first draw, where he wants a green, there are still 8 green marbles out of 17. But once he draws, we assume he's drawn his green marble. Okay. How many marbles are left? Or what's the probability then of drawing a black after he's removed a green marble?
Yes.
3 out of 16. Yes, because there's still 3 black marbles in there, but now there's only 16 marbles in the bag. And so this time, when we multiply, top of our fraction is going to be the same. And the bottom of our fraction is going to be different because it's going to be 17 times 16. Or 272. Those fractions are kind of hard to compare because those numbers, those are fractions that are, when you get a large number in the denominator, it gets difficult to think about what that really means. But if you turn 24 out of 72 into a decimal, we can reduce that fraction to 3 over 34. And then we can ask my calculator to turn it into a decimal, and we get 0.088. And that would be 8.8%. And you may go, that's not really that much different. And you're right, it's not a huge difference, but it is a difference in the probability. And so the difference between problem 3 and problem 4 that makes the difference in how you calculate it is the fact that in number 3, he puts the marble back. He restores the bag to 17 marbles before he draws his next marble. And in number 4, he doesn't put the marble back. And so the bag is not the same condition that it was before the first draw. So problems 3 and 4, some people call these compound probability. Okay, do we have questions for me on 2, 3, or 4? All right, number 5 is just for fun. What is the probability of drawing out a yellow marble out of Chad's bag?
0.
Kanisha says 0. And why, Kanisha?
If there is no yellow mark.
Very good. D also agrees with 0. It is 0% because there's no yellow marble in the bag. So that would be a way you could get a 0 probability, is set up a scenario like drawing out marbles and then there isn't the color that you asked. All right. We have about 15 minutes left. And I just want to show you what's in the rest of the packet and then we can work for a little bit. But if you look, you've got pages 4, 5, and 6. Okay, pages 4 and 5 are practice problems. Okay, and page 6 are the answers for everything that we've looked at today. Okay, so we're not going to have time, which I didn't expect we would. We're not going to have time to do together all the problems on pages 4 and 5. But I would highly encourage you to work through them. And I've provided the answers as well as explanations and descriptions of how to get to the answer. I can pretty well guarantee you will see at least one problem, this probability on the GED math test, at least one. Okay. And so and the nice thing is, like, this is the whole content. If you can master what we did today, you're going to get those 1 or 2 problems correct. And so this is like a topic, I picked it for this reason, because we can get quick points with learning a simple, maybe not simple, but at least a topic we can hopefully grab a hold on to pretty quickly.
Actually, it was a lot simpler than I imagined.
Okay.
I just needed like seconds of impression.
Yep. Kanisha's saying she just needed to brush up. This isn't that hard. She can do this. I hope you're feeling the same way. So take a look at page 4. And I'm going to give you like 10 minutes. See how far you can get on page 4. If you get done with page 4, go to page 5. And then in the last 5 minutes, we'll discuss these problems. And we're not going to have time to go through every single one of them, but at least get you started and make sure we've got some, we work out any of the kinks while we're here together. Okay. Okay, in this last 5 minutes, I don't know how far you got, and that's okay. In these last 5 minutes, let's take a look at, go through these, hopefully maybe get this first page talked through so that you can walk away feeling confident, you kind of know what you're doing. Okay, so our number cube, our die, we have 6 sides, and it wants to know what's the chance of tossing an even number. Now, even numbers are numbers like 2, 4, and 6. So there are 3 desired outcomes. That is, there's 3 possibilities that we want that would satisfy us, either rolling the 2, the 4, or the 6. And there are 6 total possible outcomes because there's 6 sides. And I can make that into the fraction 3/6, which reduces to 1/2, 50%, which can be written as 1/2. Thoughts or questions about that one? Okay, that's basically like flipping a coin. Half of your outcomes meet what you want. Okay, and number 2, our spinner has 5 equal sections, which I won't be able to draw very well. 1, 2, 3. Oh, that's only 4. Okay, so pretend those are all the same size. 2 sections are white and 3 are blue. If it helps you to sketch a picture. Okay. And so what is the chance of not spinning white? Hopefully you saw that not in there. So not spinning white would be these sections over here. So there's 3 possible not white sections out of a total of 5 sections. And this time they put the answer in percent form. And so 3 out of 5. I can change that to a percent. I push the green second key and the key that has the percent over it. That is 60%, which makes sense because there are more sections that are not white than sections that are white. Good job, ladies. I just saw your answer, Dee and Victoria. All right, number 3, he has 20 pennies in his pocket. 8 of them were minted in 2001. So if he chooses a coin at random, what's the chance it was minted in 2001? Well, there's 8 pennies that meet our criteria. There are 20 pennies in the pocket. And if we look, our answers are in percents. This one is one you might be able to pick the answer without actually calculating it. 8 out of 20 is less than half, right? So we can eliminate C and D. Okay. And 8 out of 20 is just a little bit less than half. Okay. And so you might be able to actually just estimate and get 40, or you can put 8 out of 20 in your calculator and tell it you want a percent back. And it is 40%. So always, always, always make sure you eliminate answers that are unreasonable. Because then if you have to guess, then you're more likely to get the answer right. And good job, Dee and Victoria. All right, number 4, Melanie is one of 25 employees at Kimball Electronics. The company plans to choose 3 employees at random. What's the probability that Melanie will be chosen? What'd you say?
1.
Well, there's 3 places. Okay, so she has 3 chances to be chosen out of how many? out of 25. Okay, that is much less than 50%. So we can eliminate D. Okay, and so if I put in the calculator, the fraction 3 on the top and 25 on the bottom. Second, close parentheses, it says I'm going to take that fraction to a percent. And it will tell us that that is 12% or A. All right, number 5, he's playing a card game. If one card is chosen at random, what's the chance the chosen card will have a value equal to or greater than 4? And so let's find the cards that are equal to or greater than 4. Well, this card and this card are equal to 4. Greater than 4. Almost all the cards are equal to or greater than 4. There's 8 total cards. And 1, 2, 3, 4, 5, 6 of the cards meet our criteria. And if you reduce 6 out of 8, you'll get 3/4. And you can do that in the calculator. You bring in a fraction, 6 on top, 8 on the bottom. And if you just hit enter, it will reduce the fraction for you to 3/4. And then number 6, 250 customers drop their business card in a box. 1 card is drawn per day. So if she drops in her card, she has her name in there 1 time out of a total of 250 cards. It's not very often, but occasionally you will see these written with that colon between it. This is the same thing as 1 to 250 or 1 in 250. So D would be the correct answer. You probably won't see that it written that way. But if you do, that's equivalent to that fraction. Most likely you will see fractions or percents for answers to probability problems. Okay. I hope those made sense to you. And page 5, these include problems, also problems that where you have multiple things happening, a series of events. So make sure you take some time to practice on 1 through 6 as well on the next page. And again, the answers are on page 6 with some explanation. If you get stuck, or you just want to work with a teacher on these, remember that we have the afternoon workouts from 1 to 3 or 4, where you can either go to the Flagstaff classroom, come to Page Classroom, or log in on Zoom, and you could get assistance with this if you need it. Okay. I hope you have a fabulous day. Thank you for joining us, and hope to see you tomorrow.
Thank you, Mary. Great lesson. I'm going to share the quiz that is from social studies. I'm encouraging people to memorize a list of dates before the end of the summer session.
Okay.
So if you're ready to take this poll, please take it. And if you look on the class materials for social studies, you'll find a document with the dates that I want you to know. It's very important to have some dates of US history. So do you want to take the poll? Go ahead.
All right. Are you going to stay on for a bit then, Marianne?
But I'll stay on. Can you see the poll?
Yes, it's on my screen.
Okay, yeah, anybody who feels that they know these dates or want to just try it and see which